Hello everyone and welcome to the coronavirus edition of our Theory of Signals class. On the last two lectures we talked about four types of Fourier transform. Here I have a handout which summarizes all of these Fourier transforms. This is the summary of the continuous time Fourier transform. This is the formula for the forward transform and this is the formula for the inverse transform. This is an example of a signal and this is its spectrum. Now remember that the continuous time Fourier transform is used for continuous aperiodic signals and its spectrum is continuous aperiodic. If the signal is real, we have a symmetry in the spectrum and this is how we write that symmetry mathematically. This is the summary of the Fourier series. This is the formula for the coefficients of the Fourier transform, which is essentially a forward transform, and this is the formula for the Fourier series, which is essentially an inverse transform. Remember that the Fourier series are used for continuous periodic signals, and their spectrum is discrete aperiodic. And if the signal is real, we have that symmetry in the spectrum. And this is how we write that symmetry mathematically. Now this is the summary of the discrete-time Fourier transform. This is the formula for the forward transform and this is the formula for the inverse transform. The discrete-time Fourier transform is used for discrete aperiodic signals and its spectrum is continuous periodic with period of 2 pi. And this is how we write that periodicity mathematically. Now if the signal is real, we have that symmetry in the spectrum. And because the spectrum is periodic, this symmetry repeats itself. And this is how we write that symmetry mathematically. This is the summary of the discrete Fourier transform. This is the formula for the forward transform and this is the formula for the inverse transform. The discrete Fourier transform is used for discrete finite length signals, or we can use it for discrete periodic signals. Its spectrum is discrete and periodic, with period equal to the length of the signal. This is how we write the periodicity mathematically. Now again, if the signal is real, we have that symmetry in the spectrum, and because the spectrum is symmetric, that symmetry repeats itself. And this is how we write that symmetry mathematically. There is one more interesting thing to note about this handout. Take a look at these signals, this one, and this one. They're almost the same. This signal was created by sampling of this signal. And take a look at the spectra. This spectrum is essentially the same as this spectrum in the interval from -pi to pi. And then this interval repeats itself because this signal is discrete. And this signal is the same as this signal, and take a look at the spectra. This spectrum is only a sampled version of this spectrum. Now there is a useful mnemonic which can help you to remember the properties of this spectra. The thing is that continuity is always connected with aperiodicity and discreteness is always connected with periodicity. So, if we have a signal which is continuous, its spectrum is going to be aperiodic. If we have a signal that is discrete, its spectrum is going to be periodic. And it actually works the other way around. If we have a signal which is aperiodic, then the spectrum is going to be continuous. If we have a signal that is periodic, then the spectrum is going to be discrete. And it also works for spectra. If the spectrum is continuous, then the signal is aperiodic, and so on and so forth. Now let's check it out over here. We have the discrete-time Fourier transform and the signal is discrete and aperiodic. So the spectrum needs to be periodic and continuous. Go ahead and check out these properties for all types of the Fourier transform. Now if you ever want to become good engineers, you need to know this handout as the back of your hand. So go ahead and study it. Here I have some basic formulas that go with the Fourier transform. The first formula we kind of talked about when we did the Fourier transform, the continuous time Fourier transform of a pulse. There I showed you that when I make this pulse more narrow, the spectrum will get wider. I can make this signal more narrow by multiplying the time by 2. And here I have a derivation which shows you what happens when I multiply time by a general constant a. To analyze this, we need to write down the definition of the Fourier transform and substitute the signal. Then we need to make this simple substitution. When we do that, we get this integral, which is essentially just a continuous time Fourier transform of this signal, except now it is being evaluated at frequency omega over a. So what we get is the spectrum except at frequency omega over a. So the moral of the story is that when we make the time run faster by multiplying it by some constant, the spectrum will get wider. Here I have a derivation which shows you what happens with the spectrum when I time shift my signal. Again, to analyze this, we need to write down the definition integral and substitute our signal. Then we need to make this simple substitution, which when we evaluate, we get this integral. In this integral, we'll need to take a look at this exponential, and we need to split it into two exponentials. Then we need to take this exponential and extract it in front of the integral. When we do that, we will get this integral. And when you take a look at it, this integral is just a simple continuous time Fourier transform of this signal. So the result is this exponential multiplied by the spectrum of the signal. So again, the moral of the story is when I time shift the signal, in the spectrum, I will keep my spectrum except it is being multiplied by this exponential. So you can see that some phase shift is being introduced. This formula actually shows you a trick how you can shift your spectrum in frequency. This is kind of useful. For example, take your mobile phone. Your mobile phone will record your speech, which is a fairly low frequency signal. Then it needs to encode it and shift it to a very high frequency that can be transmitted through an antenna. To do that, it will use something which is based on this formula. So the trick is, you take your signal, you multiply it by this exponential, and this is what happens. This is again just the definition integral with my signal substituted. Now in this integral I need to combine these two exponentials, which will give me this exponential, and then the whole integral is again just a continuous time Fourier transform of this signal, except at frequency omega minus omega naught. So what I get is the spectrum at frequency omega minus omega naught. So the moral of the story is, if I multiply the signal in the time domain by this exponential, I will get a frequency shift in the frequency domain. And this formula is just a reminder, when you take the Fourier transform of a Dirac delta pulse and you crunch the integral, you will get number 1. Now these formulas were derived using the continuous time Fourier transform, but very similar formulas can be derived using other types of Fourier transforms. And I would almost encourage you to try it on your own and do that. Now these formulas are not critical for us at this time, but you will very likely encounter them in the future. So it is a good idea to study them right now, so that when you do encounter them in the future, you will not be scared so much. Previously, I was talking about the properties of the Fourier transform and how we can use the Fourier transform to examine the spectral content of a signal. Now, I will be talking about how we can use the Fourier transform to alter the spectral content of a signal. Specifically, I will be talking about the filtering in the spectral domain. And I will motivate this by a problem that we commonly encounter in biological signal recording. Say we have a person. This person has a heart, and we would like to record the electrical activity of this heart. We would like to record so-called electrocardiogram or ECG. This is what a normal ECG looks like, but because the electrical activity of a heart is really weak, this recording gets often corrupted by many sources of interference. Probably the most common source of interference is so-called power noise interference, which comes from the power distribution network, from all those outlets with those 230 volts in them. This gets capacitively coupled into the body of a patient, and then it appears appeared in the ECG recording. So instead of an ECG recording which looks like this, you will get a recording which looks like this. And here you can see this periodic waveform which is close to a sine wave at 50 Hz, and that is the power noise superimposed to our ECG recording. Now our task is to get rid of that power noise. So here I have again a plot of an ECG corrupted with a power noise interference. And it is actually very difficult to remove that power noise interference in the time domain because the power noise interference is corrupted pretty much every sample of a signal. But let's take a look what happens when we take our problem into the spectral domain. I will take my signal and compute its Fourier transform, and this is the spectrum that I get. This part of the spectrum is just a normal ECG, and then at the frequency of 50 Hz I have this spike. Remember that power noise interference is very close to a sine wave at 50 Hz, so its spectrum is essentially just two Dirac delta pulses. One is at 50 Hz, the other would be at minus 50 Hz. So in the spectral domain, I will get a very good separation between the spectrum of the ECG and the spectrum of the power noise. So here I could very easily delete the power noise. But how do I mathematically delete the power noise? Well, to do this, I will create this function h of omega, which is unity everywhere except a narrow band around the 50 Hz. And to get rid of this power noise interference, I will take my spectrum and multiply it by this function h of omega. And when I do that, I will get this altered spectrum, and you can see that everything was kept except this narrow bandwidth around 50 Hz was zeroed out. So now I have a spectrum where the power noise interference is removed. Well, that is very nice and dandy, but I would like to have my signal in the time domain back. Well, that is very easy. If I want my signal in the time domain, all I need to do is just to take the inverse Fourier transform, and that will give me my ECG in the time domain, but this time with the power noise interference removed. So this is the filtering in the spectral domain. I take my signal, I compute its spectrum. Now I'm in the spectral domain, and now I will apply this function h of omega. I will multiply my spectrum with this function h of omega, and I will get my altered spectrum, and then using the inverse Fourier transform I will move back to the time domain and I will get my filtered signal. This is the entire process written mathematically. So what do I need to do? I take my signal, I compute its Fourier transform, and I will get my spectrum. Then I will multiply my spectrum by this function h of omega, and I will get my altered spectrum. And now I will take that altered spectrum, compute the inverse Fourier transform, and I will go back to the time domain and I will get my altered or filtered signal. But now I have to admit that I was cheating a little bit. I was pretending that this signal is continuous in time, and I was approaching it as if I was using continuous time Fourier transform. But in reality, this signal is going to be discrete, and as I have told you, the continuous time Fourier transform is mostly good for theoretical computations and for torturing students. If I want to use this in the real world and this signal is discrete, I need to use the discrete Fourier transform. But the sequence of steps with the discrete Fourier transform is very similar. Here you have the mathematical description of that filtering with the discrete Fourier transform. You just take your signal, you compute the discrete Fourier transform, and you will get your discrete spectrum. Then your discrete spectrum needs to be multiplied by some function h of k, and you will get your altered spectrum. Then you take your altered spectrum, compute the inverse discrete Fourier transform, and you will get back your filtered signal in the time domain. Now you can see that the filtering that I perform is decided by the shape of this function h of omega. This function will decide which frequencies will be passed and which frequencies will be suppressed. So let's take a closer look at this function h of omega and let's examine what kind of filtering we can actually achieve. First, this function h can be used with different types of Fourier transform. We can use it with the continuous time Fourier transform, in which case we would use this argument of lowercase omega. We can use it with discrete time Fourier transform, in which case we would use this argument of uppercase omega, and we can use it with the discrete Fourier transform, in which case we would use the argument of k. In all of these cases, we will refer to this function h as the frequency characteristic or frequency response. Now, what can this frequency characteristic do? On the previous slide, I have shown you that it can suppress a band of frequencies, but the frequency characteristic does not have to be this binary. It does not have to only pass or suppress some frequencies. It can actually look something like this. So it can amplify some frequencies and it can attenuate some frequencies. And I'm pretty sure that most of you have already seen a frequency characteristic that looks like this. Take a look at this picture. Does it look familiar? Well, that is just a graphic equalizer. And when you change the settings of this graphic equalizer, you are changing the attenuation of, for example, your music at different frequencies. So by changing these settings, what, for example, your mobile phone does is that it applies this shape of frequency response to the spectrum of your music. This is just a snapshot from my mobile phone, and I'm pretty sure you have a very similar graphic equalizer in all your mobile phones. So go ahead, try to play with it, and you will be able to hear how the frequency response changes the spectrum of your music. Now, the frequency response is not limited to changing only the amplitude of your spectrum. It can change the phase as well. And I'm illustrating that in this example. So here I have a frequency characteristic that is this complex exponential. And let's take a look what this complex exponential will do to our spectrum. So here I have my spectrum and I'm multiplying it with the frequency response. So my spectrum has magnitude and phase, so I can write it like this, magnitude, phase, and here I multiply it with my frequency response. And what happens? Well, when I combine these two exponentials, I will get this formula. And here you can see that I will retain my magnitude spectrum. There will be no change in magnitude, but there will be phase shift. So this frequency response will introduce phase shift. But what exactly does this phase shift do? What will happen when I will take a signal in the time domain, then I will apply filtering in the spectral domain, and I will go back to the time domain? What will be the result? Well, I will examine that here. So my signal in the time domain will be given as the inverse Fourier transform of the spectrum of my original signal multiplied by the frequency response. So here I will evaluate that integral. Here I just substitute for the frequency response, and I will combine these two exponentials into a single exponential. Now, when you take a look at this integral, you will see it is just the inverse Fourier transform of the spectrum of my original signal, except it is at time t minus uppercase t. So what I will get is my original signal except at time t minus uppercase t. So what this frequency response does is that it introduces a time shift. Overall, the frequency response can introduce some change in amplitude and phase of my spectrum. And here I will show you how this can happen simultaneously. So here I have the spectrum of my original signal, and here I multiply it with the frequency response. And the spectrum of my original signal has some magnitude and phase, so I can write it like this. And the frequency response also has some magnitude and phase, so I can write it like this. Now I can combine these two magnitudes here, and I can combine these two exponentials here. So you can see that the magnitude of my altered spectrum is given by the magnitude of my original spectrum that is multiplied by the magnitude of the frequency response. And you can see that the phase of my altered spectrum is given by the phase of my original spectrum, to which is added the phase of the frequency response. So the magnitude of the frequency response is responsible for changing the magnitude of my original spectrum, and the phase of the frequency response is responsible for changing the phase of my original spectrum. A common nomenclature here is this. The frequency characteristic is a complex function, and its magnitude we call the amplitude frequency response, and its phase we call the phase frequency response, or you can use characteristic instead of response. We recognize different types of frequency characteristic depending on which frequencies are being predominantly passed. If the frequency characteristic predominantly passes low frequencies, we talk about a low-pass filter. If high frequencies are being predominantly passed, we talk about the high-pass filter. If just a band of frequencies is being predominantly passed, we talk about a band-pass filter. And if the frequency characteristic just stops a band of frequencies, we talk about a band-stop filter. Now, I have simplified these frequency characteristics as much as possible. I'm showing you only the positive frequencies, and I pretend that I can use the continuous time Fourier transform. But we have to realize that if the signal is real, we need to have some symmetry in the spectrum with a complex signal. When I use the discrete-time Fourier transform, the spectrum will get periodic. And you need to learn to recognize that with the discrete-time Fourier transform, this is the frequency characteristic of a low-pass filter. You need to take a look at this basic period from -pi to pi, and not to get confused by the repetition of this basic period, which happens because of the discreteness of the signal in the time domain. With the discrete Fourier transform, you will get a frequency characteristic similar to the one which you get with the discrete time Fourier transform, except with DFT, the frequency characteristic will be sampled at discrete points. So with the discrete Fourier transform, this will be frequency characteristic of a low-pass filter. In MATLAB, you will be working with this interval of the frequency characteristic, so you need to keep this symmetry. And if you break this symmetry just by one sample, you are going to end up with a complex signal in the time domain. Now, the filtering in the spectral domain has some disadvantages. Before you compute those Fourier transforms, you first need to record your entire signal. This can present some problems with memory storage, especially on small devices, and the filtering cannot be done in real time. You first need to record your signal, and then you can do the filtering. You cannot do the filtering as the input data is coming in. The shortcomings of the filtering in the spectral domain can be overcome by transforming it into what is called filtering in the time domain. And here I will show you how this transformation can be done. So I will start with the filtering in the spectral domain. That means that I will take my signal, I will compute its spectrum, then I will multiply it by the frequency response, and then to get my result in the time domain, I will compute the inverse Fourier transform of this entire expression. Now I will do the rest of the derivation using the discrete-time Fourier transform, but it can be done with different types of Fourier transforms obtaining very similar results. So in the next step, I will write down the definition of this Fourier transform and this inverse Fourier transform. So first, this Fourier transform. I need to take my signal. This is my signal, except I have changed the time index from n to m. I will explain why I have changed it later. Now to complete that Fourier transform, I need to take my signal and multiply it by this complex exponential, and then take the sum from -infinity to +infinity. And this entire expression is the Fourier transform, the discrete-time Fourier transform of this signal. Now, what do I need to do? I have the Fourier transform and I need to multiply it by the frequency response. So here I'm multiplying by the frequency response. The next step is to take this entire expression and compute the inverse Fourier transform. So let's do that. This is the inverse Fourier transform, this integral from 0 to 2 pi from my entire expression. And for the inverse Fourier transform, I'll need to multiply by this complex exponential. Now here you can see why I had to change this index from n to m. I already have index n here, and I can have different numbers here and here. This, for example, can be 25, and this can be -17. So I cannot use the same letter for this index and this index. Now that I have written the entire expression using these integrals and sums, I need to rearrange it a little bit. So first I need to combine this exponential and this exponential into this exponential. Second, I need to change the order of summation and integration. So essentially I will take this sum in front of this integral, and although I can take this signal in front of that integral because this signal does not depend on the integration variable. So I can write this. I will have sum, then my signal x comes here, and here comes the rest of the expression. Now take a look at this integral. This integral is only the inverse discrete time Fourier transform of my frequency response, except at time index n minus m. And here I have it spelled out. So it is the inverse Fourier transform of my frequency response at time n minus m. And I will denote this as lowercase at time n minus m. And when I denote it like this, I can write the final expression so that it is the sum from minus infinity to plus infinity of my signal x time this function lowercase h at time n minus m. So instead of computing these Fourier transforms and doing the filtering in the spectral domain, I can replace this with this sum. Now I have copied this sum here, so I can write that my filtered signal is this expression. Now this expression has a name, and we call it the linear convolution. We denote it by a star, and we can write it like this. This is the convolution of x and h, or we can write it like this. This again denotes the convolution of this sequence and this sequence. If we do a change of variables in this sum, we can actually rewrite that sum into this form. So we can also write the linear convolution like this. Now this linear convolution is a fairly cryptic expression. We are taking our signal and we are multiplying it by some function h, and we are doing this sum. But the thing to remember is that this is equivalent to the filtering in the spectral domain. So basically all that this does is that it changes the spectrum of our signal. It can amplify some frequencies, it can suppress some frequencies, or it can introduce some phase shifts. And that is the thing to remember. The linear convolution is nothing but filtering, and filtering just alters the spectrum of my signal. As I have told you, I have done this derivation with the discrete time Fourier transform, but if I did it with the continuous time Fourier transform, I would get a result like this. This is the formula for the continuous time linear convolution. The formula looks like this, or if you do the change of variables, it looks like this. Now let's have a closer look at the linear convolution. To simplify things, I will assume that my function h of n has finite number of non-zero values. I will assume that for negative time, my function h of n is 0, then from 0 to m I will have some non-zero values, and the rest of the samples is 0 as well. In this case, the formula for the linear convolution actually gets simplified. As I go with m from minus infinity for all the negative values, this h of m will be 0. That is, I'm talking about these 0 samples. The first non-zero sample that I will get here is for m is equal to 0. And for m is equal to 0, I will get this. For m is equal to 1, I will get this. For m is equal to 2, I will get this, and so on and so forth, all the way to lowercase m being equal to uppercase m, that is this sample, and for that sample I will get this. Then for lowercase m greater than the uppercase m, I will get these zeros again, and this will not contribute to the sum. So if I have finite number of non-zero values here, the linear convolution will simplify to this formula. And this formula is often used to compute filtering the linear convolution in digital electronics. So in your mobile phones, computers, this is the formula that is being used. And because this formula is being used a lot, we often even draw it in a schematic form. So let's take a look at how we can draw this linear convolution, this filtering, as a schematic. First, let's take a look what kind of signals we have. Here we have our signal. Then again, we have our signal delayed by one sample. Then we have our signal delayed by two samples, and so on and so forth, all the way to our signal delayed by capital M samples. So how do we get these signals? We will start with our signal which is not delayed, and then we will use a delay element. This delay element is nothing but a simple memory that will keep my value for one clock cycle, and at the output I will get my signal delayed by one sample. Then I will use another delay element and I will get my signal delayed by two samples. Then I will use other delay elements and I will get delayed versions of my signal all the way to my signal being delayed by capital M samples. Now what do I need to do next? I need to take my signal which is not delayed and I need to multiply it by h of 0. And here I do that. Then I need to take my signal which is delayed by one sample and I need to multiply it by h of 1. And I'm doing that here. Then I need to take my signal delayed by two samples and I need to multiply it by h of 2. And that is being done here. And so on and so forth all the way to my signal delayed by capital M samples, and that I need to multiply by h of capital M, and that is being done here. The last thing I need to do is to add everything up. That is being done here, and I will get my filtered signal. Now this structure, as I told you, is very common in digital electronics, in your mobile phones, in your computers, and it has its own name. We call it a linear FIR filter. Now I will explain what that FIR means in a minute. Before going into that, I just want to point out that the number of delays that corresponds to that number of capital M is called the filter order. So what is this FIR? And let's have an even closer look to this function h of n. To examine it, let's put this Dirac delta pulse to the input of our filter. This Dirac delta pulse has zeros for negative time. So for negative times, I have zeros coming into the input of this filter. And these zeros are passing through this delay line, like this. So before the time 0, this delay line is filled with 0, and the output of the filter is just 0, because I'm just multiplying zeros by something and I add it up, so I will end up with 0. And that is what you can see here. This is the output of the filter, and for negative times you can see that the output is 0. The first change will happen at time 0. When the time 0 comes, before that, these values shift, and number 1 comes to the input, that is this number 1. Now what is the output of the filter? Here I will multiply this h of 0 by 1 and add it to all of these zeros. So what I will get at the output is just h of 0, and that is what I have here. Now for time n is equal to 1, first these values will shift. And a 0 will come at the input. This 0 will come to this input. So what will be the output in this case? Well, in this case, I'm multiplying this h of 1 by 1, and all those other paths are just contributing zeros. So my output will be h of 1, and here you have it. This is my output at time 1. Now what happens at time 2? Well, these values will again shift. and 0 comes to the input. This 0 comes at the input. So my output will be h2 multiplied by 1, and that is h2. And that is what you can see here, h2. Now this process will repeat itself. This number 1 will travel through this delay line, and at each position it will output this multiplier h of n. At last, this number 1 will come to the end, and now the output will be h of capital M, and that is what you can see here. Now that number 1 will fall out of the filter, the delay line gets filled with zeros again, these zeros, and the output will be 0 again. And these zeros you will be able to see at the output. So, when you feed this structure, this filter, with a Dirac delta pulse, the output will be the values of h of n. And because those values of h of n are the response to a pulse, we call that h of n impulse response. Now, depending on this impulse response, we recognize two types of filters. If the number of non-zero values of the impulse response is finite, like we have it in this case, we call the filter finite impulse response, or FIR. Or we can talk about FIR system. If the number of finite values of the impulse response is infinite, then we talk about the infinite impulse response filter, or IIR filter, or IIR system. Now, important thing to remember is that this is not just a play with numbers. This impulse response is not just a bunch of meaningless numbers, but this is related to that filtering in the spectral domain. So it is important to remember how this impulse response is related to the frequency response, because the frequency response characterizes that filter. It tells us which frequencies are amplified, which frequencies are suppressed, and what kind of phase shift we can have in that filter. And remember, what is that relationship? Well, we had that when we derived that filtering in the time domain. We had that on this slide. Here we denoted that the inverse Fourier transform of the frequency response is our impulse response. So the relationship between the frequency response and the impulse response is the Fourier transform. And when you know the frequency response, this is how you can compute the impulse response. And when you know the impulse response, this is how you can compute the frequency response. And this actually gives you tools for analysis and synthesis of filters. If I give you a filter and I will tell you what this impulse response is, you can just compute the Fourier transform and you can tell me what is its frequency response, and from that you could be able to tell that it's a low pass filter, high pass filter, that it, for example, can be used to suppress power noise interference. The other way around is that you will come up with a frequency response. For example, you will get a frequency response that will suppress your power noise interference, and by using this formula you can get proper impulse response that you can use in a schematic like this to do the filtering in the time domain. Actually, this process of designing a filter in the time domain is a little bit involved. I will be talking about it on the next lecture, but the main idea is this. Now, the last thing to mention is that this structure can work in real time. As those numbers are coming in, something immediately appears at the output. To tell you the truth, this typically introduces some time delay, and typically this is set to be the half of the number of these delay elements. The time delay is very often half of the order of the filter, but In contrast to the filtering in the spectral domain, you do not have to wait for your signal to be recorded and filter it after. The signal is being recorded as the data is coming in. Also, you do not need to store the entire signal. As those numbers are coming in, they are passing through these delay elements, through these memories, and once a number gets here, it falls out of the filter, it's forgotten, and you do not have to store it anymore. Here I have an example where I show you how you can analyze a filter if you know its impulse response. So here I have my impulse response, it's a very simple one, and when I have this simple impulse response, the convolution of my signal with this impulse response turns out to be this very simple expression, which has this very simple schematic. So basically what that filter, what that convolution does, it just computes the difference between two subsequent samples. But what does that filter do with my signal? Well, to find that out, I need to find out what my frequency characteristic is. And to find what my frequency characteristic is, I need to compute the Fourier transform of the impulse response. And I'm doing that here. This is just the Fourier transform of my impulse response. And when I compute this Fourier transform for this very simple signal, I will get this. This number 1 for time 0 will come here, this is the time 0, and this minus 1 will come here, and it is for time 1, so you have 1 here. Now I need to alter this expression a little bit. I will extract this e to the minus j omega over 2 in front of a bracket, and this is what I'm left with inside the bracket. Now check it out. When I multiply these two exponentials, I will get e to the 0. And that is what I have here. And when I multiply these two exponentials, I will get e to the minus j omega, and that is what I have here. Now you can see that this leads us to a sign, and this is the final formula. So this is my frequency characteristic of this filter. So to find out what this filter does, I'm especially interested in the magnitude of the frequency characteristic, because the magnitude will tell me how the amplitude of my spectrum is being amplified or suppressed at different frequencies. So first I will find the magnitude of this frequency characteristic, and that is here, and then I will plot it. Now I need to interpret this frequency characteristic, and to be able to interpret it, I need to realize that it was computed using the Discrete-Time Fourier Transform. So what is important here, my basic period is from minus pi to pi, and then this period repeats itself. So I need to take a look at this period, and here I can see that those low frequencies are being suppressed and those high frequencies are being passed, even amplified a little bit. So this is actually a sort of a high pass filter. And this concludes our fourth lecture from the Theory of Signals class.